Young's modulus formula we derived in the last class. Y is equal to FL divided by A into L. So work done by the force in stretching the wire gets stored in the wire as its elastic potential energy. Bulk modulus is equal to hydraulic stress to bulk strain. So what is hydraulic stress? It is again F by A, and bulk strain is nothing but delta V by V. Hello everyone. Welcome to session 4 of the chapter Mechanical Properties of Solids. This is Swati, Faculty of Physics, Vidhyaashram University College, the Temple of Excellence, Mysuru. Dear children, in the last session, we have discussed about modulus of elasticity. What is modulus of elasticity? It is denoted by K, which is nothing but the ratio of stress to corresponding strain. And also, we had discussed about the types of modulus of elasticity. What are the different types? So, the types of modulus of elasticity are Young's modulus, rigidity modulus, and bulk modulus. And next we have discussed about compressibility. Compressibility is denoted by K, which is nothing but the ratio of bulk modulus. And also applications of elastic behavior of materials. So what are the uses in real time? What are the applications of elastic behavior of materials? Why we have to study the elastic properties? Why should we have the knowledge of elastic behavior of materials? What are its real-time applications? All these things we had discussed in our last class, and also the concept called buckling. So what is buckling? What type of pillars or the materials we have to choose for the reliability of constructions? And also we had studied about the lateral strain. So lateral strain is nothing but change in diameter to its original diameter, and also we had discussed about the Poisson's ratio. So Poisson's ratio range is generally lies from 0 to 0.5. For most of the metals it ranges from 0.2 to 0.4. So all these things we had discussed in our last class. So now we are moving on to our next topic, that is elastic potential energy. So what is the meaning of elastic potential energy? What is the expression for elastic potential energy? So let us consider when a wire is under tensile stress. So now you all know what is the meaning of tensile stress. Stress is nothing but force that acts per unit area, and tensile stress is nothing but force that changes the length of a wire. So when a wire is under tensile stress, work done against the interatomic forces. Work is done against the interatomic forces. We all know that there will be a interatomic forces between the atoms in a solids. If we have to stretch the wire, which means that we need to do some work on the interatomic forces, so that we are trying to deform the object. So when a wire is under tensile stress, work is done against the intermolecular forces. So this work, whatever we do to stretch it, the work whatever we do to deform a body or to bring a difference between or against the interatomic forces. So whatever the work we do on the wire against the interatomic forces, that work is stored in the wire in the form of elastic potential energy. So the external work what we do on the wire to bring a change inside the wire, that work done is stored in the wire in the form of elastic potential energy. So let us now write the expression for elastic potential energy. So let us consider a wire of length L and area of cross section A. So the length of wire is considered as L, and the area of cross section of the considered wire is given by A. Let us take small L. This L be the increasing length. You can choose L, or you can even write delta L, which is nothing but the change in length. So it depends on, in the final expression, whatever the terms you are considering in the initial steps, that should be there. Okay. So small L I have considered here. Let L be the increasing in length when a normal force F is applied on the wire. When we apply some force, there causes a stress. Force that acts per unit area is nothing but stress. So when the stress is applied, the wire will get stretched, which means there will be a change in length, correct? The change in length is given by the letter small l. Next, if Y is the Young's modulus of the wire, you know what is Young's modulus? It is nothing but the ratio of longitudinal stress to longitudinal strain, or you can also write tensile stress to tensile strain. Correct? So Y is the Young's modulus of the wire. Then Young's modulus formula we derived in the last class. Y is equal to FL divided by A into L, where Y is the Young's modulus, F is the force applied, L is the initial length of the wire, and A is the area of cross section of the wire, and small l is the extension or the change in length. So from this we can write the expression for force also. So we have to write the expression for force, which means F equals, multiply these terms, so you will get YAL divided by capital L, that is the original length of the wire. So from Young's modulus we are writing the formula for force, F is equal to YAL divided by L. Now, the total work done. What is the total work done in increasing length of a wire? Let us see. So, the total work done in increasing L length of the wire is given by W is equal to integral of 0 to L. So, now to calculate total work done in increasing length, we have W is equal to integral of 0 to L F into DL. What does it mean? Which means we need to calculate what is the total work done in stretching a wire, in changing the length. So, the formula to find, so the work done is given by W stands for work done, and which is equal to integral of, this is called as symbol of integration, integral of 0 to L. What is the meaning of 0 to L? These two are limits, and this is generally called as upper limit and this is the lower limit. So why we are writing the limits? Because when the extension is 0, from here what is the total work done till the wire stretches to this amount. That is the meaning of writing these limits. Means initially the wire will be having length capital L, which means the extension is 0. So from 0 to bring the change in length, that is change in length is small l, I have considered here and I explained you. So up to this length, what is the total work done we need to calculate. So symbol of integration I am writing here because integration is nothing but adding the parts, adding the quantities. So when you add, when you sum up everything, you will get the total work done. Correct? So total work done W, which is equal to integral of 0 to L F into DL. So what is this F into DL? This is force acting on the wire, and DL is nothing but change in length, small changes in length. So if you integrate this small things, you will get total work done in the wire in increasing the length. Yes, now it is clear to all of you, I think, why we have to consider these two limits. So now we have the expression for force as well. So from this we can write F is equal to YAL divided by L. So let us now write W is equal to integral of 0 to L. In the place of S I am writing these terms, that is YAL divided by L into DL. See here, the Young's modulus of the wire is constant, it will not change. Because Young's modulus is different for different materials, I have considered one material wire whose Young's modulus is constant. So you cannot integrate, and the area of cross section is also constant. The length, the original length is also constant. Only thing which is changing is small l, that is the extension. As you stretch it more, it will get extended more. So that is varying. All the other terms are constant, so I can take it outside because constants cannot be integrated. So W is equal to YA divided by L, 0 to L, and remaining thing is L into DL. So now the expression becomes W is equal to, W stands for work done, YA divided by L, and integral of 0 to L, and change in length can be integrated. So I am writing it inside. The remaining part I have taken it outside because those are constants and I cannot integrate it. So L into DL. That is what the expression is written here. So next we have to integrate this. So to get the expression for total work done, you have to integrate this. So let us integrate this one. So look at this. It is of the form 0 to L, L into DL. Look at this carefully. Now looking at this, it is of the form integral of x power n dx. This is the standard form, integral of x power n dx. Here we have L power 1, n is 1 here, no power means it is nothing but 1, so L power 1 dl. Both are alike, correct? So now integral of x power n dx is given by the formula x to the power n plus 1 divided by n plus 1. So this is the standard formula. So in this way, if we integrate this, what do we get? We get, see here, in the place of x I have to write L, in the place of n I have nothing here, which means I have power 1. So it is 1 plus 1 as it is I am writing, and divided by n plus 1, again it is 1 plus 1. So here in the place of x, what do I have? L. So x to the power n plus 1 we have. So in the place of x we have L. So the formula becomes L to the power, n is nothing but 1 here, 1 plus 1 divided by n plus 1 is again 1 plus 1. So this can be written as L square, 1 plus 1 is 2 divided by 1 plus 1 is 2 again. So it will become, when you integrate this, integral of 0 to L, L dl, when you integrate this, you are getting L square divided by 2. Here we have considered only upper limit but not lower limit, because see, the limits are given here. While integrating you need to apply the limits, which means in the place of variable, first you have to apply upper limit, then you have to subtract that with application of lower limit. Since the lower limit is 0 here, I have only one term, that is L. So in the place of this variable, what is the variable here? It is L only. So in the place of variable I am taking only the upper limit. So that gives you the result L square divided by 2. So after integration you need not to write limits here. So what you get after integration, it is YA divided by L into L square by 2. So this is the expression for work done. So now it is nothing but, it can also be written as, see here, YAL into L square divided by 2 can also be written as W is equal to half into YAL divided by L. How we got this? So look at this, I have half here, so I can write it as W is equal to half into YA divided by L. I have L square here, so 1 L I can write here, L I have written like this. So you'll get half into YAL divided by L into L. So why we have to write in this form only? Because we can reduce this to a single term called F. In the previous slide I have shown you F is nothing but YAL divided by L. So to write in this form, I have taken the expression as half into YAL divided by L into small l. So this YAL divided by capital L is nothing but the expression for force, and this becomes W is equal to half F into L. So this is the expression for work done. So work done by the force in stretching the wire gets stored in the wire as its elastic potential energy. So the elastic potential energy is denoted by the letter U. What is the expression for elastic potential energy now? It is nothing but the same expression, because we know that this work done in stretching a wire will be stored in the form of elastic potential energy. So U is equal to, U stands for elastic potential energy, U is equal to half into F into L is the expression for elastic potential energy. So what is this F? F is nothing but force, and L is nothing but the change in length or the extension produced in the wire. So it is written as half into force into extension. So this is the formula for elastic potential energy in a wire. Now let us write the expression for potential energy per unit volume, or it can be called as energy density, or it can be called as energy density. In deforming a body, what do you mean by deforming a body? It means that change in shape or size of a body. So in deforming a body, what we have to do to bring any change in a body, we need to do some work, correct? So work has to be done by the applied force. If we apply some force, there causes stress, which results in strain, correct? So we have to bring a change in a body, means we need to apply some force. So we need to do some work. How to do the work? By applying a force. So this work done appears as elastic potential energy is what we derived in the last expression. And now consider a wire of length L. Again I am considering a wire whose length is L. and the area of cross section is A. So to bring the change, what we have to do? We need to apply a force. So let F be the stretching force applied and L be the increase in length. Increase in length, you can write it as small l or you can even write it as delta L. So if you write it as delta L in the final expression, you will get delta L only. So delta L be the increase in length of the wire. So now the work done on the wire is nothing but average force into increase in length. How we got this? Because in the previous expression we derived that W is equal to half into F into L, where F is nothing but the force and increase in length is given by small l, that is a change in length. We have written average force, which is nothing but 1 by 2 into F. So this can be written as work done W is equal to F by 2 into L, which is nothing but the same expression what we have derived in the last slide. The work done is stored as elastic potential energy is what we derived, which is nothing but U in the volume V of the wire. The wire will be having some volume, so the volume V of the wire, that is the work done is stored in the form of elastic potential energy in a wire whose volume is V. So that expression is given by U is equal to half into F into L. This is what we derived. And volume of the wire. So we are talking about now the expression for elastic potential energy per unit volume. So we need to define volume also. So volume of the wire is given by area of cross section into length, because we know V is equal to L cube, correct? So L cube we can write it as L square into L. L square is nothing but area. Formula area into L. So V is equal to area of cross section into length. So now area of cross section of the wire we have considered it as A, and L, original length, is considered as L. So V is equal to A into L. Now elastic potential energy per unit volume. Elastic potential energy is given by U. Per unit volume we are writing. So we are writing the expression for U divided by V. Don't get confused. U is nothing but elastic potential energy per unit volume we are calculating, and this U by V is nothing but I am taking it as small u. So elastic potential energy per unit volume is considered as small u, which is nothing but potential energy divided by volume, which means elastic potential energy per unit volume. So elastic potential energy formula is half into F into L, and volume is given by A into L. So it becomes, so what happens? Half into F into L divided by volume is A into capital L. Or we can write it as half into, we can write separately F divided by A into the remaining terms, that is L divided by L. So what is this F by A? F by A is nothing but force per unit area, that is the definition for stress, and L by L is change in length to the original length, which is nothing but strain. So elastic potential energy per unit volume is given by small u is equal to half into stress into strain. This is the formula for elastic potential energy per unit volume. So next we have a demonstration experiment for you all, that is how to calculate the Young's modulus of any material. So in many of the numericals or in many of the examples you will be getting the Young's modulus value, but how to calculate the Young's modulus value? For that we have a simple demonstration experiment, and let us now go through this. So describe an experiment to determine Young's modulus of the material of the rod. So this is the experimental setup for determining the Young's modulus of a material. You can observe there are two wires. One is the reference wire, the other one is the experimental wire. Okay, so experimental arrangement to determine Young's modulus of a material under tension is as shown in the figure. What is the meaning of under tension? It is nothing but the stretching force. You can observe loads are attached to these wires, which creates tension in the wire. Okay, so this is the experimental arrangement. Two identical wires of same length and same radius suspended side by side from a rigid support. So you can observe a rigid support over here. So two identical wires we have taken. Identical means the same kind of. So same kind of materials whose length are same initially, and also the radius is same. These two wires are attached to a rigid support is what we can observe. So the reference wire A carries millimeter main scale M and a pan to place the weight. So this is the reference wire. So this reference wires, it is attached with the millimeter and also a pan to place the weights. So main scale, it is denoted by M. Okay. So next, experimental wire B also carries a pan. You can see here, this is the experimental wire, because by keeping one wire as a reference, we are varying the load in the experimental wire so that we can find the extension producing in the other wire. So this is the experimental wire, which is also attached to a rigid support and which is also with a scale pan in it to place the loads. So experimental wire B also carries a pan in which known weights can be placed. Vernier scale V is attached to a pointer at the bottom of the experimental wire, which helps to find the elongation of the wire. As I told you, you can observe a small scale over here that is called as vernier scale. So about vernier scale you are going to study in your practical sessions, which gives us the value of small units. So vernier scale is attached to a experimental wire, because as we keep on increasing the load, as we keep on changing the load in the vernier scale, the known mass, the known weights are actually placing to the vernier scale to find the small changes in length of the wire, to find the elongation produced. So both the wire are given an initial small load to keep straight and initial reading is noted. So initially what happens, so initially what do we do is, initially both the scale pans are loaded with a small weights, because to keep the wires straight and to be stretched. Now experimental wire is gradually loaded. Now after that what happens, you can observe here, to the reference wire we have only single load, and to the experimental wires you have many loads here, which means initially they are placed with a single load because to keep them straight, and later gradually will keep on increasing the weight, or we keep on increasing the load to the experimental wire. What happens if the loads keeps on increasing? There will be a stretching in the wire, correct? So now the experimental wire is gradually loaded with more weights and reading is noted. And the reading is noted, which means as we keep on increasing the load to the experimental wires, there will be a small change in the length and those readings are noted. The difference between two reading gives elongation delta L of the wire of initial length L and radius R for a load mass M. What happens if we take the readings gradually as we increase the load? It gives us the difference between these two wires, correct? Because as the loads increase here, there will be a elongation in the wire produced. Now taking the difference of the initial reading and the reading after the load is added, that gives the difference. The difference is nothing but the elongation. Now the Young's modulus of the material of the experimental wire is given by, we know the formula to find the Young's modulus, that is y is equal to mgl divided by pi r square delta L. So how do we get this formula? That is from y is equal to fl divided by a into delta L. We know this because F by A is nothing but longitudinal stress. So because Young's modulus is nothing but longitudinal stress to longitudinal strain, longitudinal stress is given by F by A and divided by delta L by L we have. So transposing that, we will get FL divided by A into delta L. F is nothing but force, that is given by mg, and L as it is we have. A is nothing but area of cross section, that is pi r square into delta L. We have the formula for Young's modulus mgl divided by pi r square into delta L. So from this what we can conclude is y is equal to mgl divided by pi r square delta L. So from this what we can conclude is Young's modulus of any material can be determined by knowing these values, that is the mass and acceleration due to gravity. The value is known to all of us. Initial length delta L, what is the change in length that we are observing, and pi value we all know, and r is the radius of the wire. So by knowing the length, radius and the elongation that is producing in the wire, by knowing all these values, Young's modulus of any material can be determined. Suppose if I say the Young's modulus of steel is so and so, how to calculate that? You can demonstrate this experiment. How is the value given? So how is the value can be calculated? By conducting the experiments like this, by changing the loads and finding the elongation produced, we will get to know about all these parameters, and the Young's modulus of any material can be determined. So this is about the determination of Young's modulus of material. So this is all about your theory part of mechanical properties of solids. So in these sessions, what we have learnt is what is a rigid body, what is a deforming force, restoring force, stress, types of stress, strain, types of strain, Hooke's law, and how Hooke's law says that stress and strain are directly proportional to each other, stress strain curve, modulus of elasticity, types of modulus of elasticity, applications of elastic behavior of materials, and few practical applications also we have learnt, and also about how to determine the Young's modulus of material. So from all these concepts, we will come to know that how all these things are related to us in our daily life, real time applications, and that is why studying about the mechanical properties of solids is very important. So this completes your theory part. In the next sessions, we will be discussing about numericals related to all these concepts. So to solve numerical questions, we must know about the formulae what we have come across all these sessions. So I have a list of formulae now in my next session. So in this chapter, we have studied about stress is the first concept. So stress is nothing but force by area, that is given by F by A, and writing the formula is important parameter in solving a numerical. At the same time, writing the unit for the answers also very important. So the SI unit for stress is Newton per meter square, or it is nothing but Pascal. So next, strain. Strain is nothing but change in dimension to original dimension. So there are three types of strain. One is longitudinal strain, where we can say that change in length divided by original length, that is given by delta L by L. Strain has no unit, no dimension, because we have same dimension both in numerator and denominator, and hence they cancels out. So next is shearing strain. It is given by delta x by L, which is equal to tan theta. Sometimes tan theta is, since the angular displacement is very small, this tan theta can be written as theta. So this formula becomes theta is equal to delta x by L is the formula for shearing strain. So next one is volume strain. Volume strain is nothing but change in volume to original volume, that is delta V by V. And also we studied about Hooke's law. Hooke's law states that stress and strain are directly proportional to each other. So to remove this proportionality, we need to introduce a constant. So you can write it as stress is equal to K into strain, where K is called as modulus of elasticity. So modulus of elasticity K can be written as stress divided by strain. Next, we have studied about the types of modulus of elasticity. Among the first one is Young's modulus. So Young's modulus is given by force per unit area divided by change in length to original length, because Young's modulus is nothing but the ratio of longitudinal stress to longitudinal strain. Longitudinal stress is given by F by A, and longitudinal strain is change in length to original length. So it can be written as Y is equal to F by A divided by delta L by L, or it can be written as Y is equal to FL divided by A into delta L. So next, rigidity modulus. The formula to find the rigidity modulus is F by A into theta. And next we discussed about the bulk modulus and also compressibility. Compressibility is denoted by the letter K, which is nothing but the reciprocal of bulk modulus. So to find compressibility, we must know what is bulk modulus. Bulk modulus is equal to hydraulic stress to bulk strain. So what is hydraulic stress? It is again F by A, and bulk strain is nothing but delta V by V. Correct? Or we can write it as F by A into V divided by delta V. Correct? So this goes to numerator and this becomes delta V, and this goes to numerators, and it can be written as F by A into V divided by delta V. So what is this F by A? It is nothing but pressure. It is V divided by delta V. This is the expression for bulk modulus. And to find compressibility, we need to take the reciprocal of this bulk modulus, that is nothing but 1 by B, and we get 1 by delta P into delta V by V, which means we are taking the reciprocal for this expression. Next, we have lateral strain. We have studied about lateral strain, which is nothing but the change in diameter to original diameter. So change in diameter is nothing but delta D, and the original diameter is D. It is represented with the negative sign because as the length increases, as the material stretches, the diameter decreases, and hence it is denoted by a negative sign. So lateral strain is given by minus delta D by D. And we have studied about the Poisson's ratio, which is given by sigma is equal to lateral strain to longitudinal strain. Lateral strain is nothing but minus delta D by D, and longitudinal strain is delta L by L. So these are the formulae what we have studied in this chapter, mechanical properties of solids. So in the upcoming sessions, we are going to solve numericals based on these formulae. So until then, take care all of you. See you all in the next session. Thank you.